Okay, so lesson 2.3, polynomial functions and their graphs. We are going to learn how to identify equations of polynomial functions. That's pretty easy. Recognize characteristics of graphs of polynomial functions. Understand the relationship between degree and turning points. We'll talk more about this in a second. Determine end behavior of polynomial functions. Use factoring to find zeros of polynomials. Identify zeros and their multiplicities, and then graph them. Okay, so here's the idea. Definition of polynomial. It's basically a big long expression like this where things are added and subtracted, but the key is that the exponents must be a whole number. So notice how the exponents here are all whole numbers. This one's a 1, and when there is not one, it's like being a 0. So this is a definition of a polynomial. They must all be whole numbers. They must also be positive. So positive whole numbers. All right, so it must be greater than or equal to 0 and not a fraction or a decimal. So are these polynomials? Is this one a polynomial? This one right here?
No.
It is not a polynomial because we know that this is a negative exponent. So no, it is not a polynomial because of that negative exponent. This one over here?
No.
No, because we have fractional exponents and negative exponents. So again, no, not a polynomial. How about this one right here?
Yes.
Good guess. No exponent here. It's like an exponent of 0, 2, 3. Boom. This is a polynomial. All right, pretty easy there. All right, so basic polynomial graphs. What do they look like? Does anyone remember what this looks like? If you watched yesterday's podcast, you should know what the graph of x squared is called.
It's the U.
The U. Technical term, U is not a technical term. It's called a parabola. Parabola. That is y equals x squared, or f of x equals x squared right there. X cubed, how about that? What does that look like?
That's the little,
It's a thingy.
the little S looking thing.
The little S looking thing. The cubic function looks like that. Kind of like a tangent function, right? That's a cubic function. I drew it a little too steep right there. Let me fix that. That is the cubic function, pass through 0, 0. But so generally speaking, if you have a random polynomial, so it's continuous, it's smooth, so it doesn't have sharp edges. It's continuous, it keeps going forever in both directions. And it could have a number of turns. So this is some other random polynomial. Those are supposed to be smooth, rounded edges, not like a sharp edge like that. That would not be a polynomial. This is an example of a polynomial right here. Okay? Smooth and continuous, rounded edges. Rounded edges. Okay, so what we're going to be doing today basically is figuring out from the equation of a polynomial, we want to be able to draw a rough sketch. And to do that, we need 3 pieces of information. We need to know how many turns it has, the number of turns. We need to know its end behavior. And we need to know what its x-intercepts and zeros are. So number of turns is somewhat self-explanatory. It's how many times this thing turns around. So like this one over here would turn 1, 2, 3, 4 times. So we have 4 turns. This has 0 turns. It doesn't turn around at all. This one has 1 turn. That's what I mean by number of turns. You don't have to write that down. We're going to go over these specifically. End behavior. What does the graph look like at the edges? Like as x gets really big or as x gets really small. And third is, what are the x-intercepts or zeros? You probably are familiar with x-intercepts. It's where and how does the graph interact with the x-axis. And we're going to go over each of these individually, starting with number of turns. Okay, so number of turns. How do we determine the number of turns of a polynomial? Well, it's all about the degree of a polynomial. So can somebody, in the number of turns, must always be less than or equal to the degree minus 1. The degree minus 1. So basically, if the degree is 3, then you could have 2 or fewer turns. If degree is 3, that means 2 or fewer turns. Because remember, we're not looking for an exact sketch. We're looking for a rough sketch. So we can be fine with 2 or fewer. And generally speaking, we're going to go, if the degree is 3, we're going to draw it with 2 turns. 2 turns. All right. Can somebody tell me what the degree of this first example here is?
3.
Alexa, 3. Why 3?
Because the degree is the highest exponent.
Exactly. This is the highest exponent. That's what the degree is. Highest exponent. So we know the degree is 3, which means how many turns would we draw this thing with?
2 or less than 2.
Yeah, we're going to go with 2 turns. So 3 equals 2 turns. So when whatever this looks like, we're going to draw it with 2 turns. 1 turn, 2 turns. That's what I mean by a turn, where the function turns around. It changes from increasing to decreasing. We also could have drawn it the other way, down then back up like that, because we don't really know yet how to differentiate between these two. Either of those are good options for 2 turns. You'll see this one has degree of 2. Degree equals 2, so that would mean just 1 turn, which makes sense. If we start it over here and then draw like that, it creates a parabola, which makes sense given what we know about parabolas. They come from quadratic functions, x squared. All right. Somebody tell me this one. How about Walker? 3x to the 4th plus 1. What's the degree of that?
4.
Degree is 4, which means how many turns would we draw it with?
2.
Degree minus 1, so
3.
3 turns. 3 turns. So if I were to draw this, and again, don't really worry about anything besides the turns for right now. So we might start from down here, and we turn 1, 2, 3 times. So there would be our polynomial, something like that. That's how we do number of turns. Basically, degree minus 1. The reason why I talk about less than or equal to, like this whole or fewer component, is because remember x cubed over here? You would think that would have 2 turns, right? Because it was a degree of 3, but it has 0. So there are occasions where it could have fewer than 1 less, but we're just going to go with 1 less when we're drawing our rough sketch. All right, second. Am I going too fast? Are we okay? Thumbs up or thumbs down? I can see you all now.
We're good.
We're okay? All right. Okay, so second thing we need to know, so in addition to how many turns it has, is its end behavior. End behavior. So end behavior answers this question up here. What is happening to the function as x approaches infinity or as x approaches negative infinity? So that's just a fancy way of saying, if we have a graph here, and I'll just use this graph down here, and then I'll erase it. Basically, as x approaches infinity, we know we're going this way. So essentially, we know for all polynomials, they'll either be going up or going down as we move to the right. And it'll do the same thing as we go to the left. It'll either be going up or it'll be going down. The way we describe that in common terms is we'll either say it rises or it falls. It rises or falls as we either go right or left. So I'll show you what that means in a second. So you're going to pick one of these two. Maybe it's like rises as we go left or falls as we go right. I'll explain in a second what that means and how that's going to look. Okay, so how do we determine what's happening as we go left and right? Well, two things. What the degree of the function is, and not what it is, but whether it's even or odd, and the sign of the coefficient of the highest degree term. So it's a lot of words, but it just means basically, is the highest degree term, does it have a positive coefficient or a negative coefficient? All right, and I'm gonna go through the four different combinations of even, odd, positive, and negative to show you what they would look like. All right, so for this first one, the degree is 2, so that would mean it's even. Degree is 2, so it's even. The leading coefficient is 3, so that means that is positive. Just going to write a plus from here forward. So that means if the degree is even and the leading coefficient is positive, the end behavior is rises right and rises left. Rises right and rises left. You want to have this written down. When it's even, positive, rises right, rises left. So what that would mean is that as we go to the right over here, we know our function would be going up like that. As we go to the left, it also rises. It might do some weird stuff in the middle depending on how many turns there are and what our x-intercepts are. But this is all we know about this function from this right here. So positive, rises right, rises left. Okay? Now, guys, for these parts right here, I'm about to go through 4 examples, and then I'm going to put them in a chart. So if you want to just wait to write them down until we get to the chart here, that might be an easier way to go about this. Okay. So this second example. Now, before we go on, actually, 2 things I want to remind you of. Remember back these 2 functions right here? I went over these because these predict what the end behavior was. Remember, this is even degree with a positive leading coefficient. Notice how this one goes up and up, right? Just like this one did, up and up. So when it's even and positive, it looks the same thing as x squared looks like, which we know just looks like this. That's an easy way to remember these. And I'll review this in a second as well. So what's different about this other one? Somebody tell me. Jared, what's different about this next example compared to the first one? What's our degree?
It's even.
Even, since it's still 2. So our degree is still 2. And what's different about this one compared to the first one? What's the leading coefficient?
It's negative.
It's negative. Can you predict what the end behavior might be? Are we going to be going up and up or down and down?
Probably down.
Down and down. Because remember, if we figure out what negative x squared looks like, that just looks like the upside down version of positive x squared. So we know it goes down on each side. So the way we describe that is falls right and falls left. Okay? So falls left and falls right when it's even and negative. And again, you don't have to write these down yet. I'm going to put them all in a chart at the end. Okay. Next one. Jace, tell me, degree of this one. What's the degree of this polynomial right here?
3.
It's 3.
3. So degree is 3. Katya, you can do the next one after this. Degree is 3, which means it's odd. Jace, sign of the leading coefficient, positive or negative?
It's positive.
Positive. So the end behavior can be predicted by another function with a degree that's odd, that has a positive leading coefficient. Jace, do you remember what y equals x cubed looks like? As we go to the right, where does it go? Up or down?
It goes up.
Up. How about as we go to the left, where does it go?
It goes down.
Exactly. Guys, you finding this useful? The fact that if you know what x cubed looks like, you know what an odd positive one does. So we know it's going to rise right, rises right, and it's going to falls left. All right, Katya, help me with this last one. What's the degree of this one?
3.
3. So that means it's odd. Okay, how about what is the sign of the leading coefficient? Positive or negative?
Negative.
Negative. So what would you guess compared to what we know about this one? How is the end behavior gonna change?
Rise left, fall.
Yep, it's gonna switch. So it rises left
Woo!
and falls right. Good job. Okay, so guys, that's the basic idea. Notice how the end behavior is unaffected by how many times a polynomial graph turns. All it answers is what is happening at the edges. That's end behavior. Let's summarize it real quick. Okay, here's a chart that will be useful for you. So when the degree is even and it's positive, it kind of is going to look like x squared, which we know goes up to the left. Didn't draw that very well. Up to the left and up to the right. When it's even and negative, it's going to look like negative x squared, which goes down to the left and down to the right. When it's odd and positive, it looks like positive x cubed, which hopefully you know goes down to the left and up to the right. And then finally, when it's a degree is odd and the leading coefficient is negative, it's going to look like negative x cubed, which does the opposite of positive x cubed, up to the left, down to the right. I'm going to type in, I'm going to type these in as well, just the rising. Let's see. So we know it rises right and rises left. This one is going to fall both ways. Falls right, falls left. This one rises right and falls left. And this last one rises left and falls right. All right, I'm going to stay on this page for a moment so you guys have some time to get that down. Actually, take a picture with your phone if you need to, if you haven't written it down yet. And then we'll go on in about 10 seconds. All right, so we've talked about end behavior. We talked about how many times a graph turns. The last thing we need to be able to sketch the graph are the x-intercepts. X-intercepts. So what is an x-intercept or a zero? These are different, they're synonyms for each other. Another synonym for it is actual root as well. When you see the term root, that means the same thing as x-intercept or zero. So what is an x-intercept? Sterling, what's an x-intercept? Do we know?
It's where the line crosses in the x part of the graph.
Yeah, so where the curve intersects the x-axis.
Yep.
Perfect. And the x-axis is which one? The up and down one or the left and right one?
The left to right.
Yes, that's our left-right axis. Okay, so that says left, right, that chicken scratch right there. Okay, so how do we find them? Well, if I give you a graph, that was pretty bad. If I give you a graph and I say, here's a graph right here. The x-intercepts are simply the points where it touches or crosses the x-axis. So those would be our x-intercepts. That's not the way we're going to be doing it. I'm going to be giving you a formula or an equation for a graph, and you have to come up with them algebraically. So what are ways that we find x-intercepts algebraically? Well, we're going to be using our polynomial solving tools. And those are like quadratics, like factoring. And the quadratic formula. Those are the main two that you'll need to use. Factoring and the quadratic formula. That's what we're about to practice right here. Okay, so let's do an example. Actually, before we do an example, let's talk about what a couple things mean. All right, so we know zeros are x-intercepts. Well, there's something called multiplicity as well. And what multiplicity is, basically if you have multiple zeros at the same x value. Let's say, for example, you have a polynomial that looks like this. Let's just call it x cubed minus 4x to the second. Okay, if we're finding zeros of this, what we have to do is set it equal to 0 and then solve. Well, how I would solve this is by first taking out an x squared. And then I'd be left with x minus 4. Then I'd be like, okay, how do I solve this? Well, I set each part of this separately equal to 0. Well, this x squared being 0 just means x equals 0. But there's something special about it. It has to the second power right here. This means it's x equals 0, but there's kind of two x equals 0s. Because for a cubic polynomial, I have to have 3 zeros. The zeros must equal the number of the degree, so to speak. So x equals 0, this means with a multiplicity of 2. That means there's two x equals 0s. Okay? For this one, for the x minus 4, that's just a normal one, because there's only to the first power here. X minus 4 equals 0, solve that, x equals 4. This one would not have a multiplicity, or there's only one there. So you could kind of say it's like a multiplicity of 1. But multiplicity kind of means there's more than one, so we don't say that. But you could, for understanding's sake, that's what that means. So for this example, we got x equals 0, the multiplicity of 2, and x equals 4, that's just a normal one, so it's got a multiplicity of 1. Okay, so why do multiplicities matter? Well, we know x-intercepts, as we talked about here graphically, they're the places where our function crosses the x-axis. But if the multiplicity is even versus it being odd, it changes what that intercept would look like. So essentially, it determines if it'll cross the x-axis at that spot or bounce off the x-axis at that spot. It'll bounce at odd multiplicities. It will cross at even multiplicities. So let's look at this green one over here. An even multiplicity at x equals 2. That would mean when we factored, we would have gotten like x minus 2 squared and then some other stuff equals 0. Because this would have been x equals 2 with a multiplicity of 2 because of that exponent. So we know it would, x equals 2 is right here. But instead of crossing through, our function will bounce off the x-axis in a not a sharp way, in a kind of curved way. Can't draw this very well. So it kind of bounces off like that and then keep doing its thing. So that's what an even multiplicity at x equals 2 would look like. Notice how it bounced. It might be up here as well. It might be up there as well. Okay, so we know it bounces at odds, crosses at evens. Well, an odd multiplicity at x equals -3, x equals -3 would be like right over here. And we know if it crosses, that just means if it's up here, then it'll cross down there. If it's down here, it would have done the same thing and cross. You can only do one or the other, can't do both. So we might have, if we had already been up here, we would have gone down like that. That's the basic idea. So it crosses. I did those in reverse. Hold on, I have this written backwards, guys. It bounces at even and crosses at odd. Bounces at even multiplicities. See that? Bounces at the even multiplicity, crosses at the odd. Any questions about that now that I said that backwards? Are we all good with the correction?
Yeah.
Okay. I had it written backwards originally. So even multiplicities, it bounces. Odd multiplicities, it crosses. Okay. Let's find some zeros. Let's practice finding some zeros. Okay. So can anybody tell me what the first step to finding the zero is? I'll take a volunteer. Just start talking.
Can we take out an X?
We can take out more than just one x. How many x's can we take out?
3 X's.
Yeah. So we can take out x cubed. So x cubed comes out. This one had 5 x's. So how many are left when I take 3 of them?
X squared.
Yep. X squared minus that one had 4 x's. So there's 1 left. This one had all 3 x's. So what's left?
Plus 1.
Plus 1. Yes. Remember, don't leave off that plus 1. There's a 1 implied in front of there. You can't just drop it completely. Okay. So I'm finding zeros. Guys, what's up with this one? Can I factor this more?
You can.
Yes.
What am I looking for when I factor a trinomial like this?
You want to complete
Something that adds to -2 and multiplies to 1.
So adds to -2 and multiplies to +1. Okay, what two numbers add to -2 and multiply +1?
-1.
-1 and -1. So that means this is still x cubed, because that's just chilling. And then we've got an x minus 1 and another x minus 1. How can I write that?
X minus 1 squared.
Exactly. X cubed, x minus 1 squared equals 0. You don't have to do this, because you could say, x equals 1 and x equals 1 from those two. Which means when there's 2 of them, that means it's going to be x equals 1 with a what?
Multiplicity of 2.
Multiplicity of 2. This one, we say x cubed equals 0. And remember, the way I got x equals 1 was I said x minus 1 equal to 0, add 1 to each side to get x equals 1. Okay? So x cubed equals 0. So that just means
Multiplicity of 3.
x equals 0, multiplicity of 3. Okay, so why does the multiplicity matter? Multiplicity matters because it tells us what the graph's going to do there. So we know, since this one's odd, since 3 is an odd number, we know it's going to cross at this one. Since 2 is an even number, we know it's going to bounce. So we know at 3, so we know at x equals 0, it's going to, so we know we have an x-intercept there at 0. And we've got an x-intercept at 1. 0 and 1, those are the two values at which our x-intercept occurs, okay? But because this was odd, we knew it crossed there, crossed at 0, and it bounces. What just happened?
Oh.
Woo, that was a close one. So we know it's going to cross at this one, and it's going to bounce at that one. So depending on where we are, which we're going to put all our stuff together in a moment to figure that out. Depending on where we are, whether we're up here or down here, we know we're going to cross at that one, and then we got to bounce off this one. And then we'd look something like that. Now, it could be this, or it could have been the other version, where if we had started up here, we would have crossed like this, then bounced, and then keep going. But we got to put our end behavior together with this to figure out which one of those it is. Okay? I'm going to erase that second one just for the sake of understanding. All right. So last thing, let's put them all together to sketch the graph of the function. Okay. So things we need. What was the first thing we needed? Somebody help me out. What was the first thing?
Turns.
Yes. How many turns?
2. I want 3.
Hold on. What was the second thing we needed?
The in the behavior.
End behavior. That's basically what it's doing at the edges of the graph. And then the last thing we needed was,
X-intercept.
x-intercept /0/.
yes, x-intercepts, which means the same thing as zeros or roots. Okay, let's do all three of these. All right. So, how many turns does this one have? Well, how did we know that?
Good 4 minus 1 is 3.
Yes, degree was 4. 4 minus 1 equals 3 turns. So we're going to draw this one with 3 turns. Draw this one with 3 turns. How about our end behavior? How do we know what the end behavior is? We needed to know
Even odd then.
even/odd degree, right? And we needed to know positive/negative leading coefficient.
So,
So-
even.
Let's look back at our, so this one has, what's the degree, even or odd?
Even.
Even,
Odd.
because of the fact that it's 4 right
4.
here, right? Leading coefficient. Leading coefficient's 1,
Oh, yeah.
so that means it's positive. Positive. Even degree because of the 4. Leading coefficient's 1, so positive. Okay, so we look back at our chart, look back at your charts. So we've got a positive leading coefficient and even degree. Where's our chart? Positive leading coefficient, even degree, looks just like x squared does, which we know what x squared looks like. It goes up both ways, rises right, rises left. Rises right and rises left. We'll put that together on the graph. And then lastly, we need our x-intercepts. How do we find x-intercepts again? How do we start it?
Finding 0.
Yes, finding zeros. Set the whole thing equal to 0, factor and solve. X to the 4th minus 4x squared equals 0. Now what?
Take out 2 x's.
Take out 2 x's starting out, x squared, and then we're going to have x squared minus 4 equals 0. How about this one right here? What can I do with that? Well, I know I'm going to set this equal to 0 eventually, but let's factor this one more. What does this factor into? Or can I use another method to solve this?
X minus 2. Wait, X
Completing
minus 2
square.
plus 2.
Okay, so you can do 2 things. You can factor this more. So I could make this x plus 2, x minus 2. Or because this, I could use square root method to solve this. I'll show you that down here. X squared minus 4 equals 0. Add 4. And then we square root both sides and we get x equals plus or minus 2, which we would get from this one, x equals negative 2. This one, x equals 2. All right? How about this one? I get x squared equals 0. Square root that, I get x equals 0. What about the multiplicities of this 0? What's the multiplicity of this one?
2.
Multiplicity of 2 because of the squared part of this. Neither of these are squared, either here or here. So those are both, we don't really say multiplicity 1, but I'm just going to write it just to remind us. Multiplicity 1 and multiplicity 1. So those are our 3 zeros. Or they kind of count as 4 zeros because the multiplicity of 2 kind of counts as 2. So those are our 3 zeros. Okay. Let's put this all together by putting in a graph. Where'd my graph go? There it is. Okay. So let's put all this together now for a rough sketch. All right, I know I'm going to have zeros at 0, -2, and 2. What's it going to do at each 0? Like bounce or cross? At x equals 0, bounce or cross? Bounce because of the evenness of the multiplicity. So it bounces here. These are both
Cross.
odd multiplicities, so it's going to cross at both of those.
Cross.
Okay, so I know. So I can go 2 to the left, 2 to the right, and I'm going to have dots here, here, and here. Those are my 3 zeros. I know I'm going to cross at these two and bounce at that one. Cross, bounce, cross. Just as a reminder for what I need to do. Now, we can't draw it yet because we don't know whether we're starting from down here or starting from up here. What about, how can we use this to help us put it together with this?
You start in the top left and end in the top right.
Exactly, because it rises in both directions. That means when we're going to the left, it goes up. So we know it goes up like this and up like that, just like x squared does, guys. It matches the shape of x squared. It might do weird stuff in the middle, but it goes up left and up right. Rises right and left. Okay, and now all I have to do, I don't even have to worry about how many turns it has. This will be self-checking at the end. All I have to do is follow the instructions for this. So I know I'm going to cross right here. I'm actually going to draw this a little steeper right here. So it's, actually, I'll keep it how it was just so I can show you guys. All right, so it's going to cross right here. It's going to cross right there. It's got to turn back around and then bounce. So it's got to bounce back down here, but it's got to cross there again. So it turns back around, then goes back up and through. So notice I had to turn it back around to get back to here. That's how I knew this turned back around. And then it had to bounce. I had to turn back around again. Then my next one was at 2, so I had to turn back around and go back up, and then I'm done. And notice, does it have 3 turns? 1, 2, 3. It sure does. Now, this is not the prettiest looking exponent. What it would really do is it would kind of be more, this would be going up like this and up like that. But it would be fine if you left it exactly as I have it. All right, questions? Questions, comments, concerns?
Are those 3 points going to be the 3 points for every time we graph?
Notice how we didn't really use how many turns there was to graph it. It confirmed itself that we know we're right based on that. But yes, you will use these 3 every time you graph.
I mean the 3 points on the graph that you like
Oh, definitely not. It could be anything.
the CBC you wrote or whatever this is.
Well, that was CBC because it happened to bounce and cross at those 2.
I got you.
You follow?
Yes.
Okay. For those of you that feel like you have this down, you are free to leave and start working on the homework assignment. If you want to do one more, I'm going to do one more problem with everybody.
Wait, Miss, sorry, what's the quiz on Sunday about?
So there's going to be a take-home quiz over the weekend. I'm still working on it. So it'll be open book and everything. It'll just be like kind of like a practice quiz, but it is going to count for a grade.
Okay.
Does it count for a quiz grade or what?
Yes, counts for a quiz grade.
All right.
Is it gonna be on like the safe exam?
To be determined. I'll let you guys know. I'll send out an email about it.
Let it be on civic exam.
Wait, did you say on Friday?
Sunday.
No, it's a take-home quiz, guys. It's a take-home quiz.
It's open note though, right?
Sorry?
It's open note, you said?
Yes, you
Why
can use
would
all
we
your
take
stuff.
Why would we
When
take the
is it?
civic exam thing?
So you would not be in Safe Exam Browser. It would just be like a worksheet.
Okay.
When will it be due?
Let's not worry about the quiz for right now. All right? Okay. So let's do one more practice. Unless you feel you're good with this, then go ahead and start on the homework. But I'm going to do one more practice with everybody. Let's do this one. Let's do this one.
Wait, hold up. When are our corrections due?
Next Wednesday.
Yeah, they do next Wednesday.
All right. Thank you.
Yep. All right, we're gonna do this one problem next. We're gonna do this one problem next. And I know this is a long class period, guys. I apologize.
You're good.
Okay, so a few spoilers here. Just gonna rewrite it. Negative n to the 5th plus 6n cubed minus 9n. Okay, so starting out, number of turns. We're gonna need number of turns. We need end behavior. And we need x-intercepts. Those three things we be able to graph. All right, somebody who's still here, how many turns is this gonna have?
4.
4.
4 turns. 5 minus 1, right? 4 turns. End behavior. Which of our 4 basic functions does this one most resemble?
The x cubed,
Right.
positive x cubed.
Yeah, negative the x cubed. So if you look at your chart, you'll see that it goes up to the left and down to the right. But again, all you really need to know is it's like x cubed because it's odd, and it's negative. So it's the reverse of x cubed. All you really have to know to memorize this whole deal is what x cubed and what x squared and x cubed look like. Remember, this one goes up and that one goes up, and this one's opposite that. And this one starts down and then goes up, and this one's opposite that. You don't really need to know anything else. Okay? So we know it's going to rise right, rise left, and rise right. So when we're starting our graph,
Said it falls right. Rises left, falls
I mean,
right.
sorry,
fall right.
I misspoke and miswrote. My bad. Yes, thank you, Jerron. So it rises left and falls right. So on our graph, which I'm going to grab from right here real quick. Hopefully it doesn't bring the writing with it. There we go. So on our graph already, because it rises left and falls right, I know it's going to end up going up over here and down over here. All right, x-intercepts, last step. All right, this one's a little harder. Negative n to the 5th plus 6n cubed minus 9n equals 0. Okay, what can I take out of everything? If I factor.
You can take out an
Yeah, take out an n.
Mm.
I'm going to take out a negative as well because I don't like the leading coefficient to be negative. So negative n, that reverses the signs of all of these. So it's n to the 4th minus 6n squared plus 9. Okay. And for this one in particular, this is tricky. How can we factor this? Does this factor? Does it kind of look like something that could factor like a trinomial?
No.
No.
Well, what if this was a 2?
You could add a number between the 4 and the 2.
What if I change to that? Now would it factor?
Yeah. You add
Yeah.
to 6 and multiply a -9 or positive 9.
So it still does factor. It's just when it factors, it's going to factor into n squared and n squared rather than n and n. Okay? So this is still a 4. And this is still a 2. It just has to factor the other way. So it's going to be n squared minus 3 and n squared minus 3. Okay? That's how we can factor this. So it's kind of like n squared minus 3 squared. Okay? So this one, I've got n equals 0 with multiplicity of 1. And for each of these, n squared minus 3, I can solve that. N squared minus 3 equals 0. N squared equals 3. So n equals square root of 3 and negative square root of 3. And because they were squared, they're both multiplicity 2. So those are our 3 zeros. And notice how we have one odd multiplicity, which means it'll cross here, and 2 even multiplicities, which means it'll bounce at both of these. It bounces at both of these. All right, and again, we're just doing a rough sketch. So we know at 0, it's going to cross. And then at the square root of 3, it's going to bounce. And then at the negative square root of 3, it's going to bounce. So let's draw it. Let's put our end behavior together with, we know what the x-intercepts are and what the behavior at those intercepts is. So we know we're going to bounce off that one and then cross there and then bounce again and then connect with our other 0. Let's count how many turns we have to confirm our answer from here. We're starting going down, so I got 1, 2, 3, 4 turns. And we're done. All right.
Mr. Sorry,
Yes.
unmath related, but the Falcons just dropped the new uniforms and it's awful.
They are awful.
They're so bad.
Yeah.
Disgusting.
Dude, Jerron, the fade.